Hello everyone, today we will discuss rotation of rigid object about a fixed axis. As we discussed before, an object rotates around another center. This is called circular motion. Like a moon rotates around the earth. In this case, it's called circular motion. But in this lecture, we will discuss rotation about its axis, like an earth rotates around its axis. Now, let's identify a rigid object. A rigid object is an object that has a fixed shape and size. And also, the rigid object is a collection of point masses, like particles. Which means, if the rigid object is rotating about an axis, then all points or particles of the object rotate through the same angle about the axis of rotation. Example, these particles are rotating around this axis here. Let's consider this case here. We have a disk rotating or centered around the z-axis, which perpendicular to the plane of the page here. If we take a point on the disk here, this one here, and if this one here is the x-axis and this one here is the y-axis, x and this is y. Now if we take this point here, let's name it P. Now the position for this point on the disk here is R, making angle theta. So theta here defines the angular position for this point P, and it's measured in this case here counterclockwise, from positive x-axis counterclockwise, like in this here. And theta in this case here is positive. So theta is positive if it's measured counterclockwise. And theta is negative if it's measured clockwise. Now, we will define the angular quantities using the same strategy that we used to define translational quantity. Here's translational quantities and here's angular quantities. In translational quantities, position is defined as r of t. Now, in angular quantities is theta of t. Same strategy we used before. Now, the displacement in translational quantities is defined as delta r which equal to r final minus r initial. Now the displacement in angular quantity is defined as delta theta or theta final minus theta initial. Average velocity in translational quantities is defined as delta r over delta t. Now average velocity in angular quantities is defined as omega average here, which equal to delta theta over delta t. Now average speed, which was here average, is defined as total travel distance over delta t, total distance over delta t. In angular quantities, it's defined as omega average here equal to total traveled angle over delta t. Now instantaneous velocity here in this case here equal to dr by dt. In angular quantities it's defined as omega equal to d theta by dt, this case here. Now instantaneous speed is defined as this. So omega in this case is defined as omega here. Average acceleration is defined as delta V by delta T. Now acceleration in rotational motion or in angular quantities is defined as alpha average, which is equal to delta omega by delta T. And finally, the instantaneous acceleration, it's equal to dV by dt. Now instantaneous acceleration for this case here equal to d omega by dt. As we can see here, it's comparison between translational quantities and angular quantities. Now theta is measured in radian. So theta here, it's in radian or rad, and theta in rad equal to pi over 180 degree and theta in degrees. With this equation here, we can transform radian into degrees or degrees into radian. Now, since theta in radian, the angular speed is measured in radian per second, rad per second, or other units for angular speed is revolution per second or revolution per minute. In such a way, one revolution equal to 2 pi, which equal to 360 degree. Now, angular speed is measured in rad per second or rad or revolution per second, revolution per minute. And remember, one revolution equal to 2 pi, which equal to 360 degrees. Now, angular acceleration here, angular acceleration alpha here is measured in revolution per second square or revolution per minute square. Back to the disk example here. Now let's just have x and y coordinates. So this is x, the center. This is x and this is y. And again, the z-axis is perpendicular to the page here. Now, if this disk rotates this way, the direction of the angular velocity is measured as this. You point your four fingers, this one here, with the direction of the rotational disk here, the thumb here. In this case here, your four fingers directed with the rotational disk direction, and your thumb here is directed in the direction of angular velocity. Now, if the disk rotates the other way, it's clockwise in this case here, again, point your fingers with the rotational direction, and in this case here, and your thumb directed with the negative z axis. So in this case here, omega is positive and in the z axis, and this one here, omega is negative in the z axis. Now let's find the direct relation between angular and translational quantities. Now back to the same disk example. If we have a point P here, and this is the position vector r, and this is theta. Now, the traveled distance, which is the arc in this case here, name it s equal to r theta. And the magnitude of the tangential velocity is given by v equal to ds by dt, or equal to r d theta by dt. On other words, v equal to r omega. Now again, the magnitude of the tangential acceleration, a tangent in this case here, equal to dv by dt, or in other words, r d omega by dt. A tangent in this case equal to r alpha. And since there is a rotational object here, there is a radial acceleration, and this radial acceleration or central acceleration in this case is defined as a central equal to v square over r, or r omega square. And because we have two types of acceleration, tangential and radial acceleration, the total acceleration or the magnitude for the total acceleration A is given by square root of a tangent here square plus a radial square. Notice that it's pretty much the same procedure we have done before. Just a quick reminder here, instead of using s in translational quantities, we use theta. And rather than using v, we use omega, and instead of a, we use alpha. As we can see here, we have a disk, the solid disk here, and there is a particle located at this position here, away from the center, a distance r. In this case, r is the radius for this circular path. Now this particle is moving in a circular path, as this one here. The position of this particle depends on two things: the radius of the circular path, this r here, or the distance from the center of the disk here, and on the angle theta. For that reason, we identify the position as angular position because it depends on the angle. When this particle completes one revolution, it actually sweeps the circumference of a circular path here, and the circumference of the circular path is equal to 2 pi r. Now r in this case is the radius for the circular path, and 2 pi is actually theta. So the arc here, this arc here, let's name it s, it's equal to r theta. Now when theta equal to 2 pi and r, s in this case will be the circumference of the circular path. Now as long as we have angular position, we should have angular velocity. This angular velocity is defined as omega. Now the direction of omega is as follows. If the particle moves counterclockwise, like in this one here, omega will be in the positive z-axis, or in this case, if this disk located in the xy plane, now omega will be in the positive z-axis or out of the plane. But if the particle moves clockwise, in this case here, and again this is x and y position, the omega will direct it in the negative z-axis or into the plane. Just let's mention this one here. Omega is positive if the particle moves counterclockwise, and omega is negative if the particle moves clockwise. In either case, the angular velocity does not depend on the particle position. Now the tangential velocity in this case, it's equal to r omega. Now the one that changes is the tangential velocity because it depends on the radius of the circular path. Now, as we can see here, the tangential velocity is constant because the radius for this circular path is constant, is not changing, and the omega in this case, it's 0.2 rad per second. Now, if we increase the omega in this case here, the velocity is increasing. As we can see here, it's increasing because omega is changing and the radius is fixed as before. Now, back to the equations of motion we mentioned before. In translational motion, Vx final equal to Vx initial plus axt, and x final minus x initial equal to Vx initial t plus half ax t square, and Vx final square equal to Vx initial square plus 2ax x final minus x initial, and the last one here, x final equal to x initial plus half Vx final plus Vx initial times t. Now, this is in translational quantities. In rotational quantities, again, instead of using S, we use theta, and instead of V, we use omega, and instead of A, we use R, and don't forget the proportionality constant between these two, between these quantities. So in this case here, this equation will be the same as this one here, but rather than V, we use omega. So omega final equal to omega initial plus alpha t, and in this one here, theta final minus theta initial equal to omega initial t plus half alpha t square, and for this one here, omega final square equal to omega initial square plus 2 alpha theta final minus theta initial, and the last one here, theta final equal to theta initial plus half omega initial plus omega final t. And remember, these equations are the equations of motion in translational motion, and these equations are the equations of motion in rotational motion. Let's have an example here. An electric motor rotating a wheel at 100 revolutions per minute is switched off, assuming that the wheel has constant negative angular acceleration of magnitude 2 rad per second square. Now question, how long does it take the wheel to stop, and through how many radians has the wheel turned during the time interval found in part 1? Now, the initial angular velocity in this case here is given here equal to 100 revolution per minute, and also given as constant negative angular acceleration. So alpha in this case here, it's equal to minus 2 revolution per second square. And since the electric motor is switched off, so in this case here, the final angular speed for this motor equal to 0. So W final equal to 0. Now use equations of motion for rotational motion. So omega final equal to omega initial plus alpha t, and you just substitute the numbers we have here, and t in this case here 5.24 seconds. And remember, don't forget to change minutes into seconds. Now in the second part, through how many radians, so we need here theta actually. So delta theta here equal to theta final minus theta initial, which equal to omega initial t plus half alpha t square, and you just substitute numbers here, you will find it's equal to 27.4 rad. Example, we have here two rabbits. Bonnie sits on the outer rim of a rotating disc. Clyde sits midway between the center and the rim. The disc makes one complete revolution every 2 seconds. What is Clyde's angular velocity? Now in this model we have two particles. The green one and the red one are rotating on a disc with different positions. One of the particles, the red one, in the rim, and the other one, it's a distance r from the center of the disc. If we provide different angular positions for these two particles, let's see what's going to happen. Both particles will move with different tangential velocities and different angles, as we can see here. Now, the tangential velocity for the green one is equal to this one here, v equal to r omega, and omega is, for the green one, it's 0.29, and r is, this is r here. Now, for the second particle, this one here, the omega v here, it's equal to r omega, and r in this case is this one here, this whole thing here, r, and omega in this case it's equal to 0.49. For that reason, as we can see here, this tangential velocity is greater than this one here. If we set both particles to have the same angular velocity, this one here, and the angular velocity for both particles, it's equal to 0.2 rad per second. Let's see what's going to happen here. Both particles will have same angular position, but the velocity is different for both, and it's constant for both particles, because tangential velocity for the red one, it's equal to r omega, and v for the green one, it's equal to r, let's name it omega 1, and this omega 2. Now omega is the same. The only difference here is the radius for the circular path, but the radius for the circular path for the green one is fixed, so the velocity it's equal to 0.2 meter per second, and it's not changing. And the velocity for the red one, it's 0.4 meter per second, and again it's not changing because the radius is constant. From this whole thing here, we can just conclude that the angular velocity does not depend on the position of the particle, and it's constant, but the tangential velocity is changing because it depends on the radius of the circular path as well as the angular velocity. Now remember, the angular velocity or omega of any point on a solid object rotating about a fixed axis is the same. Now in this case here, so both Bonnie and Clyde go around one revolution, which is 2 pi radians every 2 seconds. So to simply answer this question here, Clyde will have the same angular velocity as Bonnie. Now we have here, now as you can see here, this is Clyde here and this is Bonnie. Both rabbits here will have the same angular velocity. Now in the same example here, who has the larger linear or tangential velocity? Now in this case here, linear velocity or tangential velocity, it's equal to r omega. Now r here is the distance from the center. Since Bonnie has a larger distance from the center, this one here, this one here, this one here, and this one here are for Clyde. In this case here, Bonnie will have larger linear speed because it's located further in the disk. So to answer this one here, Bonnie example. Now suppose that the speedometer of a truck is set to read the linear speed of the truck, but uses a device that actually measures the angular speed of the tires. Now if the larger diameter tires are mounted on the truck instead, how will that affect the speedometer reading as compared to the true linear speed of the truck? Now the linear speed V is equal to omega r, and now since the speedometer measures the same angular speed as before, now in this case r here plays a crucial role in the magnitude of the linear speed. Now increasing the radius of the tires, as in the mentioned in the example here, will increase the linear speed V. Example: an object at rest begins to rotate with a constant angular acceleration. Now if this object rotates through an angle theta in the time interval t, through what angle did it rotate in the time half t? Now since the object is moving at constant angular acceleration in this case here, so theta final equal to theta initial plus omega initial t plus half alpha t square. Now theta initial, assuming it's starting from 0 and starting from rest, it means omega equal to 0 in this case here. Now theta final equal to half alpha t square. Notice that theta here is related with theta is related with t square, which means if t goes to half t in this case here, theta will be related with the quarter of the angle. So theta at t equal to half t equal to quarter this magnitude, half alpha t square. Example: now in this example here, an object at rest begins to rotate with constant angular acceleration. If this object has angular velocity omega at time t, what was its angular velocity at the time half t? Now remember, omega final equal to omega initial plus alpha t. Starting from rest means omega initial is equal to 0. So in this case here, omega final is related with t. Now dropping the time into a half t will drop the omega final into half omega. In other words, omega equal to at t equal t, in this case equal to alpha t. Now omega when t equal to half t equal to half alpha t. Example: a wheel rotates with a constant angular acceleration of 3.5 rad per second square. A, if the angular speed of the wheel is 2 rad per second at t equal to 0, through what angular displacement does the wheel rotate in 2 seconds? Since we have here constant angular acceleration, we can use equations of motion for rotational motion here. So delta theta equal to theta final minus theta initial equal to omega initial t plus half alpha t square, which equal to 2 rad per second times 2 seconds plus half times 3.5 times 2 square, which equal to, in this case, 11 rad, or delta theta equal to 11 rad times 57.3 degree per rad, which equal to 630 degrees. Now in the same question, through how many revolutions has the wheel turned during this time interval? Now delta theta equal to 630 degrees. Now we need to convert this degrees into revolutions, so we have to multiply by 1 revolution, and each revolution is equal to 360 degrees, and you will find it 1.75 revolutions. Now what is the angular speed of the wheel at t equal to 2 seconds? Omega final equal to omega initial plus alpha t in numbers 2 rad per second plus 3.5 times 2 seconds here, which equal to 9 rad per second. Now suppose that we have the same situation as before, but rather than moving in rotational motion, we are moving here in translational motion. So same numbers, same everything, but instead of using the rotational motion, we use here in translational motion. What is the velocity of the particle at t equal to 2 seconds? Now if we use the same numbers as given in this example here, delta x here will be equal to x final minus x initial, or equal to the initial t plus half alpha t square in numbers. And remember, same numbers, but instead of using rotational, we use here translational numbers. So 2 times 2 plus half 3.5 times 2 square, and the distance or the displacement here, delta x, will be equal to 11 meters, and the velocity will be, in this case here, v final equal to v initial plus alpha t, and with numbers v final here equal to 9 meter per second. Pay attention here, we have no translational analog as in part B, because the translational motion is not repetitive as rotational motion. Example: the angular position of a rotating object is described by this equation here, theta of t equal to 2 plus 5t plus 3t squared, where theta is in radians and t in seconds. Find the angular position at t equal to 3 seconds, and find the angular velocity at t equal to 3 seconds, and the angular acceleration at t equal to 3 seconds as well. Now theta at t equal to 3, in this case here, equal to 2 plus 5 times 3 plus 3 times 3 square, or equal to 44 radian. Now the angular velocity, omega in this case here, it's equal to d theta by dt, which equal to the first derivative of this theta here, which equal to 5 plus 6t. You substitute t equal to 3 in this case here, so the answer will be omega here equal to 23 rad per second. And the last one here, alpha equal to d omega by dt. You just derive theta one more time, and it's equal to 6. So alpha, when t equal to 3 seconds, it's constant, it's equal to 6 rad per second square. Example: a disk 8 centimeter in radius rotates at constant rate 1200 revolutions per minute about its central axis. Determine the tangential speed at a point 3 centimeters from its center and the radial acceleration of a point on the rim. Now we need to calculate the tangential speed at a point 3 centimeter from its center, so somewhere in here. So this one here, that's the point P that we need to calculate the tangential speed for that point. So R in this case equal to 0.03 meters, and in this case here the tangential speed equal to omega R. Now omega as given, it's 1200 revolution per minute, and R it's equal to 0.03 meters. So in this case here V equal to 3.77 meter per second. Now the radial acceleration at a point on the rim, so somewhere right here, we need to calculate the radial acceleration of that point. In this case here, omega equal to 1200 revolution per minute, and R in this case it's equal to 0.08 meters. Now before going through this, we have to convert revolution per minute into rad per second, in this case here, which equal to 126 rad per second, and A in this case here equal to omega square R, or equal to 1200, almost 60 meter per second square. Example: a typical compact disc player, the constant speed of the surface at the point of the laser lens system is 1.3 meter per second. Find the angular speed of the disc in revolutions per minute when information is being read from innermost first track at R equal to 23 millimeters and the outermost final track R equal to 58 millimeters. Now let's find omega initial in this case, which equal to V over R. Now initial is the innermost track here, and at R equal to 23 millimeters, so V in this case it's equal to 1.3 meter per second divided by 2.3 10 to the power minus 2 meters, or equal to 57 rad per second. Since the question asked to find the angular speed in revolutions per minute, in this case we have to convert 57 rad per second into revolution per minute by multiplying by 1 revolution per 2 pi rad, since 1 revolution equal to 2 pi rad, and seconds we have to convert it into minutes, so 60 divided by 1 minute, and you do the math here, so it's equal to 5.4 10 to the power 2 revolution per minute. Now for the outermost track, omega final in this case here equal to V over R, same rule as before, now equal to 1.3 meter per second divided by 5.8 10 to the power minus 2 meters, or 22 rad per seconds. We just convert this one here as we did in this one here, so it's equal to 2.1 10 to the power 2 revolution per minute. Now the maximum playing time of a standard music CD is 74 minutes and 33 seconds. How many revolutions does the disc make during that time? Now since we look for revolutions, in this case here, delta theta equal to theta final minus theta initial, which equal to half omega initial plus omega final times t. Now you substitute numbers. Omega initial is, we just calculated this one here, it's 57 rad per second, and omega final it's equal to 22 rad per second here, and t is given as in this one here. We have to convert this one here to seconds, so it's equal to half 57 plus 22 multiplied by 4,473 seconds. In total it's equal to 1.8 10 to the power 5 radian. Now to convert this one here into revolutions, delta theta in this case here, it's equal to 1.8 10 to the power 5 multiplied by 1 revolution over 2 pi radian, which equal to 2.8 10 to the power 4 revolutions. What total length of track moves past the objective lens during that time? Now in this case here, x final equal to the initial t, which equal to 1.3, because it's asked for total length here. Now we need to find the translational distance here, so x final here equal to the initial t, which equal to 1.3 times the total time in seconds. We just calculate this one here, 4,473 seconds here, so it's equal to 5.8 10 to the power 3 meters. What is the angular acceleration of the CD over the time interval 4,473 seconds, assuming that alpha is constant? Now alpha here, it's equal to delta omega over time interval, so omega final minus omega initial divided by t, which equal to 22 rad per second minus 57 rad per second divided by 4,473 seconds, which equal to minus 7.8 10 to the power minus 3 rad per second squares, which means the disk experiences a very gradual decrease in its rotational rate as expected. Now let's have an example. A skater spins with her arms extended. When she pulls in her arms, she reduces her rotational inertia and spins faster so that her angular momentum is conserved. Compared to her initial rotational kinetic energy, her rotational kinetic energy after she pulls in her arms must be the rotational kinetic energy here. It's equal to half I omega square, and it also equal to half L omega. In such a way, L equal to I omega. Now since L is conserved, here is conserved, it means the larger omega here will produce larger rotational kinetic energy. Now the extra energy comes from work she does in her arms. So to answer this one here, the rotational kinetic energy after she pulls in her arms must be larger because she's rotating faster. Example: two different spinning disks have the same angular momentum, but disk 1 has more kinetic energy than disk 2. Which one has bigger moment of inertia? Now here's the situation. This is disk 1 and this is disk 2. To answer this one here, the rotational kinetic energy is defined as half I omega square, or it's equal to L square over 2I. Now we used here L equal to I omega. Since L is the same here, it means bigger I will produce smaller rotational kinetic energy and vice versa. So to answer this question here, disk 2 will have bigger moment of inertia. So disk 2 have bigger moment of inertia. Example: a person holding a spinning bicycle wheel while standing on a stationary turntable. If he flips the wheel over so that it is spinning in the opposite direction, the turntable will, in this case, to answer this one here, the total angular momentum of the system is actually upward and it's conserved. Now if the wheel has negative angular momentum, which means directed downward, the table and the person both will have +2 angular momentum and directed upward. So the answer this one here, it will start to spin in the same direction as before flipping, because the person and the turntable will have +2L and directed upward. Example: a uniform rod of length L and mass M is attached at one end to a frictionless pivot. The rod is released from rest in the horizontal position. If the mass of the rod is concentrated in the middle of the rod and the moment of inertia of the rod is given by I equal to 1/3 ml square, calculate the magnitude of the initial angular acceleration of the rod. So here's the situation. So we have here, and here's the pivot, this one here, and here's the weight of that rod, and all this is the length L. Here. This one is the pivot. Now the net torque, it's actually equal to I alpha. Alpha is the angular acceleration and I is the moment of inertia. I is given for this rod here, which equal to 1/3 ml square, and in this case here the net, or the magnitude for the net torque, it's equal to R F and sine theta, and remember theta is the angle between F and R. R in this case here, it's equal to L over 2, and F in this case here is the weight of that rod, and the angle between the force and the position R, or the distance R, it's equal to 90 degrees. You substitute this back in here, you will find the net torque equal to L over 2 mg sine 90, which equal to 1 in this case, sine 90, and in this case torque net equal to L over 2 mg. You substitute this here back in this equation here, you will find that, so L over 2 mg equal to 1/3 ml square. You simplify this equation here, L square times alpha. You simplify this equation here, so the magnitude for the angular acceleration will be 3g over 2L. Now, in this example here, consider an oxygen molecule rotating in the xy plane about the z-axis. The rotation axis passes through the center of the molecule, which is also perpendicular to its length. The mass of each oxygen atom is equal to 2.66 10 to the power minus 26 kilogram, and at room temperature, the average separation between the two atoms is equal to 1.21 10 to the power minus 10 meters. And as a hint here, treat atoms like particles. Calculate the moment of inertia of the molecule about the z-axis, and if the angular speed of the molecule about the z-axis is equal to 4.6 10 to the power 12 rad per second, what is the rotational kinetic energy? Now, to calculate the moment of inertia of the molecules about the z-axis, remember I in this case here equal to summation of the mi ri square, or in this case m, and d over 2, because each atom is located a distance d over 2 from the center, plus m d over 2 square, which equal to m d square over 2. You substitute numbers here, 2.66 times 10 to the power minus 26 times 1.21 10 to the power minus 10 square divided by 2, and the answer will be 1.95 10 to the power minus 46 kilogram meter square. So this is the moment of inertia of the molecules about the z-axis. Now, if the angular speed of the molecule about the z-axis is equal to 4.6 10 to the power 12 rad per second, the rotational kinetic energy, in this case here, Kr, equal to half I omega square. We just calculated I from this part here, and it's equal to rotational kinetic energy equal to half 1.95 10 to the power minus 46 multiplied by here 4.6 10 to the power 12 square. You do the math, it's equal to 2.06 10 to the power minus 21 joule. And this is the rotational kinetic energy of the molecules about the z-axis. Example: 4 tiny spheres are fastened to the end of 2 rods of negligible mass lying in the xy plane, assuming the radii of the spheres are small compared with the dimensions of the rod. Now, if the system rotates about the y-axis with an angular speed omega, find the moment of inertia and rotational kinetic energy about this axis. And the other part here, suppose the system rotates in the xy plane about an axis, z-axis, through the origin, or calculate the moment of inertia and rotational kinetic energy about this axis. Now here's the situation here. This capital here, and the distance from the origin here, it's equal to a, and this distance here, it's equal to a, and the distance from the origin on the small m here, it's equal to b, and this one here, it's equal to b. If the system rotates about the y-axis, in this case here, iy equal to summation mi ri square, or equal to ma square plus ma square, and in this case it's equal to 2ma square. And the rotational kinetic energy, it's equal to half iy omega square, and it's equal to half 2ma square omega square, or ma square omega square. Now the fact that small m does not contribute in this moment of inertia, because they have no motion about the axis of rotation. Now with the same logic, the moment of inertia around the x-axis, it's equal to 2 small m here, and the distance b square, and the rotational kinetic energy around the x-axis, it's equal to b square omega square. Now to answer the second part of the question, when the system rotates in the xy plane about the z-axis, in this case, let's just represent the situation. So this is x and y coordinates. So the system rotates around the z-axis, as you can see in this one here. Now the moment of inertia around the z-axis, in this case, equal to ma square plus a square plus small m b square plus small m b square, or in other words 2m a square plus 2m b square. Now same procedure, the rotational kinetic energy, in this case, equal to half iz omega square. You just substitute iz from this one here, so the answer is equal to half 2m a square plus 2m b square omega square In other words, it's equal to ma square plus mb square times omega square. Example: find the moment of inertia of a uniform thin loop of mass m and radius r about an axis perpendicular to the plane of the hoop and passing through its center. Here's the situation. Here's the thin loop, and if we take a mass element dm and the radius for this loop, it's equal to r, and here's x-axis, this one here. So I, the moment of inertia around the z-axis, it's equal to integration r square dm, and it's equal to r square integration of dm, in other words, it's mr square. One more example. Calculate the moment of inertia of a uniform rigid rod of length L and mass m about an axis perpendicular to the rod and passing through its center of mass. So the situation is as this. Here's the rod, and here is the x, this one here, and this is the rotational axis. The length of this rod is equal to L. Now dm, the mass element, equal to lambda dx, or equal to m over L dx. Iy, the moment of inertia about the y-axis, equal to integration of r square dm, or equal to integration from minus L over 2 to L over 2. So minus L over 2, L over 2, x square m over L dx, or m over L integration minus L over 2, L over 2, x square dx. In other words, it's equal to m over L times x cubed over 3 minus L over 2 to L over 2, which equal to 1 over 12 ml square. Now let's define torque. Consider that we have a rod connected through another bar through this pivot point. Now this rod is allowed to swing back and forth here. If we apply a force parallel to the rod here, the blue one here, this one here, we will notice that this rod will not rotate. But if we apply a perpendicular force, let's name it F2 here, we will notice that the rod will rotate. We conclude that only perpendicular forces will exert or will cause a rotation. The perpendicular force will cause rotation. Now a torque represents the ability of a force to rotate an object about an axis of rotation, the pivot here. Now the torque is defined as torque tau is defined as R cross F. Now let's consider this case here. If a force, this one here, the green one, F, is applied on the rod here, we will see that only perpendicular component will exert a torque. Now if this is theta, here, we'll have actually two components of the force, F cosine theta, and this one here is the parallel direction of the force, and F sine theta, and this is the perpendicular one. And we will notice that only this component here creates the torque. In this case here, torque is defined as R cross F. or in other words, torque is equal to R F sine theta. In such a way, R here is defined as the vector from the pivot point, this one here, until the force F here. So this is the arm, let's name it R, and this is the force F. And theta is the angle between the force and the vector R. In other words, the magnitude for the torque is actually equal to the magnitude for the vector R and the magnitude for the vector F sine the angle between F and R. Now, to find the direction of the torque, let's use this notation. If the force rotates the object counterclockwise, then the torque is positive. So torque is positive if the force rotates the object counterclockwise. And the torque is negative if the force rotates the object clockwise. So if we have this situation here, and here's the rod, and there's a pivot point here. If the force directed this way, then the torque in this case is positive. And in the other situation, when the force, the pivot here, is applied like this one here, then the torque is negative. Now, since torque is defined as R cross F, and remember, when you cross product two vectors, the answer is a new vector perpendicular to R and F. So torque in this case is a vector quantity. And if we have like several forces are rotating the object, now this one here, let's see here, situation, and this is the pivot point here. Now if you have, let's say, F here, 1, and this one F2, this one here, 3, and this one here, F4. Now if we have several forces, F1, F2, F3, and F4 applies on this rod here, then the net torque acting on the object is the vector sum of all torques acting on that object. So for instance, the net torque in this case here equal to torque from 1 and plus torque from 2 plus torque from 3, force 3, and plus torque from 4, etc. And this is vector addition, it's not scalar addition, like this one here. Now let's have example. Two forces produce the same torque. Does it follow that they have the same magnitude? Since the torque is defined as R cross F, in other words, it's the product of the force times distance, so it could be two different forces that act at different distances could still have the same torque. So to answer this one here, no, it doesn't follow that they have the same magnitude. Example, Now, in which of the cases shown below is the torque provided by the applied force about the rotation axis is the biggest? For all cases, the magnitude of the applied force is the same. Now, as we mentioned before, this force is parallel to the distance from the pivot. In this case here, the angle between the distance here and the force is equal to 180 degree, and in this case here, no torque whatsoever can we get from F4. Now F3 here, it's with some angle with the distance here, and in this case only the perpendicular component will provide a torque in this case here, but F1 is completely perpendicular to the distance here, and in this case the torque that we will get here is the maximum. So torque equal to R cross F in this one here, and F here, and the angle between F1 and the distance R here is 90 degree, and sine 90 equal to 1. The torque here will be maximum, which equal to R F in magnitudes here. So to answer this one here, F1 will get the maximum torque. Example, when a tape is played on a cassette disc, there is a tension in the tape that applies a torque to this supply reel. Assuming that the tension remains constant during playback, how does the applied torque vary as the supply reel becomes empty? Now to answer this one here, let's imagine the supply reel, how it looks like. So this is the core here, and here's the tape around it, this like one here. Now when the supply reel empties, it means that all this radius will become decreased, and in this case the only part of this supply reel is the core itself, which is the small one here. Now in this case the distance R is decreased, which means, assuming that the tension remains constant during the playback, which means the only thing that changes is the radius of this supply reel, which means the torque will decrease. The torque will decrease. Example, in the figure, find the net torque acting on the rod about the left end if the rod is massless, and F1 as a magnitude equal to 10 newtons, F2 equal to 25 newtons, and F3 equal to 30 newtons. So in this question here, we actually look for the net torque acting on the rod. As we mentioned before, the net torque is actually the vector sum of all produced torques. So torque here equal to torque 1 plus torque 2 plus torque 3, and that's it. In this case here, let's find torque 1. So torque 1 here, it's actually equal to R1 cross F1 and R1 F1, whereas here's F1 here. And remember, only the perpendicular force applies here. So F1 in this one here, this F1, change the color here. So the only component produced torque in this case here is this one here. So F1 sine theta, which is in this case equal to 20. Now torque 1 actually equal to R1 F1 sine 20, or in this case, and remember R1 equal to 4. Remember this is the pivot here, so R1 equal to 4. So torque 1 equal to minus 4 times 10 times sine 20 which equal to minus 13.7 newtons. And remember the minus sign because the force applied clockwise, and in this case it means torque is negative. Now let's move on and find torque 2. Now same procedure here, and remember only the perpendicular force exert a torque, which means F2 cosine theory, and in this case here torque 2 it's equal to R. In this case R, the arm here is 2, R2 F2 cosine theory. We should have here sine theta, and theta here it's equal to 90. It doesn't matter actually if we just write this down or just ignore it, because sine theta or sine 9 equal to 1. You just do the math, you will find equal to 2 times 25 here cosine theory, and the answer is 43.3 newtons. And remember it's positive because the applied force is counterclockwise and the torque should be positive. Now let's move on and find the torque 3 in this case here. Torque 3 actually it's equal to R3 cross F3. Now R3 is the distance from the pivot, and here's the distance in this case here, so this is the distance here, so in this case R3 is actually equal to 0, which means no torque whatsoever from force 3. So torque here is equal to 0. So the net torque in this case here equal to 29.6 Newton meters. Now let's define moment of inertia. Moment of inertia is defined as I equal to mr square, and in this case here m is the mass of the particle and r is the distance from the axis of rotation. So the moment of inertia of system particles is equal to I equal to m1 r1 square plus m2 r2 square plus m3 r3 square plus or summation of mi ri square. Now as a generalization for this one here, the moment of inertia for rigid object can be found as I equal to integration r square dm. And remember, the moment of inertia is scalar quantity. Now let's have an example. In the figure, m equal to 2 kilograms, x equal to 4 meters. Find the moment of inertia in the following cases: if the object rotates about the z-axis, if the object rotates about the y-axis, and if the object rotates about the x-axis. So we have here x and y coordinates, this one here, like this, and we have a mass m located on the x-axis, a distance 4 meters. Distance here 4 meters, and this one here is the x-axis, and this one here is the y-axis, and the z-axis out of the plane. Now to find the moment of inertia when the object rotates about the z-axis, in this case here, so moment of inertia is actually equal to mr square, and m in this case it's equal to 2 kilograms, and r in this case, the distance from the z-axis is 4 meters, and in this case I around the z-axis equal to 2 times 4 square, which equal to 32 kilogram meter square. To find the moment of inertia if the object rotates about the y-axis, in this case here, I equal to same rule, here r square, and it's equal to, when m equal to 2 kilograms, r equal to 4 meters is the distance from the y-axis, and in this case iy equal to same answer as before, 2 4 square, which equal to 32 kilogram meter square, and the moment of inertia around the x-axis, in this case same rule we will follow, m in this case 2 kilograms, r is equal to 0 because the distance of the object from the x-axis is equal to 0, so no moment of inertia about the x-axis, so I x here equal to 0. Example: two spheres with the same radius and equal masses. One is made of solid aluminum and the other is made from a hollow shell of gold. Which one has the bigger moment of inertia about an axis through its center? Now to answer this one here, remember moment of inertia, it's equal to m r square. So it depends on the mass of the object and the distance from axis square. So both spheres have the same mass, but one of them is hollow, which means all the mass is concentrated on the outer shell. Now this is the hollow sphere, and this is the solid one, sphere. Notice that the mass of the hollow sphere is located away from the sphere center. In this case here, the moment of inertia for the hollow sphere will be higher than the moment of inertia of the solid sphere. The hollow sphere will have higher moment of inertia because the mass is located further from the center. Now let's define the relation between torque and angular acceleration. The relationship between the net torque acting on a single particle and its angular acceleration is defined as torque net here equal to I alpha. In such a way, I is the moment of inertia of the particle about the axis of rotation, and alpha is the particle angular acceleration. And the same relationship is valid also for a rigid object, which means this one can be used for a single particle or it can be also used for rigid objects. Now let's have a comparison between linear motion and rotational motion. Let's start with work in linear motion. So work is defined as, in linear motion, is the integration from x initial to x final fx dx. Now in rotational motion, work is defined as the integration from theta initial, theta final, tau d theta. Now the kinetic energy in linear motion is defined as half mv square. Now in rotational motion, the kinetic energy is defined as half I omega square, and the power in linear motion is defined as Fv, actually it's F dot V here, and the power is defined as, in rotational motion, is defined as tau omega, and the linear momentum P here is defined as mv, and the angular momentum in rotational motion, it's L here, which equal to I omega, and the last one here is the net force is equal to dp by dt, Newton's second law, and in rotational motion the net torque is defined as sum of taus equal to dl by dt. In this model, different pulleys with different shapes, like this one here, it's a solid sphere. The radius for these pulleys 1.4 meter with mass 5 kilogram, and the force it's equal to 23 newtons. Now let's see what's going to happen here. We would like to find the angular acceleration. To calculate the angular acceleration, let's see here. We applied a force on this one here equal to 23 newtons. Now this is the angular acceleration. The way we calculated this one here is as this. The net torque, it's equal to I alpha, and I in this case is the moment of inertia. Since this is a solid sphere, I for the solid sphere it's equal to 2 over 5 mr square. When you calculate this one, m is equal to 5 kilograms, r equal to 1.4 meter. Now when we calculate this, I will be equal to 3.92 kilogram meter square. Now the net torque, it's equal to R cross F. F is this one here, which equal to the tension. So this is F here, and the radius for this, it's R, this one here. The angle between the tension or the force in this case and the radius, it's equal to 90 degrees. The net torque, it's equal to RT, which equal to 1.4 times 23 equal to 32.2 Newton meter. It's right here. Now alpha, it's equal to the net torque divided by the moment of inertia for the solid sphere, which equal to, in this case, 32.2 divided by 3.92 or 8.21 rad per second square. Now let's change the solid sphere pulley into spherical shell pulley and see what's going to happen. Again, same procedure as before. We apply the force here on this spherical shell pulley, and we would like to calculate the angular acceleration. Now if we follow the same procedure as before, the net torque, it's equal to RF, and it's the same, by the way, because F and R are not changing, and equal to 32.2. Now remember, I for the spherical shell, it's equal to 2 over 3 mr square. By substituting m equal to 5, r equal to 1.4, we will find that the moment of inertia for the spherical shell, it's equal to 6.53. Now alpha here, it's equal to the net torque divided by I, and in total it's equal to 4.93 rad per second square. It's written here. Now let's change the spherical shell poly into solid cylinder. Again, same procedure, same everything. Here the only thing that changing is the moment of inertia. I, in this case, here it's equal to half mr square, which equal to, in this case, 4.9 kilogram meter square, and the torque is not changing. It's equal to 32.2 for all types of pulleys. Alpha, in this case, it's equal to net torque divided by I, which equal to 6.57 rad per second square. Now let's changing the pulley into cylindrical shell pulley. The moment of inertia for cylindrical shell, it's equal to mr square. M equal to 5 kilograms, R equal to 1.4, and I, in this case, 9.8 kilogram meter square. Tau, or the net torque, is constant. For this case, it's equal to 32.2. So alpha in this case will be equal to 3.29 rad per second square. Another example. A uniform solid cylinder has a radius r, mass m, and length l. Calculate the moment of inertia of that cylinder about its central axis. So here's the situation. Now you slice this cylinder into small cylinders with thickness equal to dr. Now the moment of inertia about the z-axis for this cylinder, it's Iz equal to integration r square dm, and it's equal to r square. Now we use here cylindrical coordinates, 2 pi rho l r dr. You integrate this one, 2 pi rho l from 0 to r cube dr, and integration for this one here, it's half pi rho l r to the power 4. And remember, rho, the density, it's equal to mass over volume, and in this case here it's equal to mass over the volume of the sphere. It's pi r square l. You substitute things together, you will get the moment of inertia about the z-axis for the cylinder. It's equal to half mr square. Now the good thing is the moment of inertia for homogeneous rigid objects or like uniform shapes, it's already calculated. Now, for instance, for cylindrical shell, the moment of inertia about its center, it's equal to mr square. Now for hollow cylinder, the moment of inertia about its center, it's equal to half r1 square plus r2 square. In such a way, r1 is the inner radius, of the hollow cylinder, and R2 is the outer radius of the hollow cylinder. Now for solid cylinder, the moment of inertia about its center, it's equal to half r square, and for rectangular plate, the moment of inertia about its center is equal to 1 over 12 a square plus b square. In such a way, a here is the width, b is the length of that rectangular plate. For long thin rod, the moment of inertia about its center, it's equal to 1 over 12 l square, and for long thin rod, with rotation axis throw end, equal to 1/3 l square. For solid sphere, the moment of inertia about its center, it's equal to 2 over 5 mr square. Thin spherical shell, the moment of inertia equal to 2 over 3 mr square. Now this means that there's no need to do any integral calculations for these known shapes like a cylinder, hollow cylinder, a solid sphere, and so on. Let's have an example. Consider once again the uniform rigid rod of mass m and length l. Find the moment of inertia of the rod about an axis perpendicular to the rod through one end. Now to find the moment of inertia of the rod about an axis perpendicular to the rod through one end, we have to use this rule here. The moment of inertia, it's equal to the moment of inertia of the center of mass here plus md square. We actually used here parallel axis theorem. So you do the math here. Moment of inertia about its center equal to 1 over 12 ml square plus now d here is the mid length, here it's l over 2 square, so in total 1 over 3 ml square. Example: a uniform rod of length L and mass M is attached at one end to frictionless pivot and is free to rotate about the pivot in the vertical plane, as in the figure. The rod is released from rest in the horizontal position. What is the initial angular acceleration of the rod and the initial linear acceleration of its right end? Now let's draw the situation. So here's the fixed part here, and here's the pivot thing here. This is mg, and this pivot part, and this whole thing is L. Now to find the initial angular acceleration of the rod, find the torque. Torque equal to R cross F. Now the arm R is this one here, R, and F here is perpendicular. In this case, the force is mg, and R in this case it's equal to L over 2. Now sum of all torques, or the net torque, it's equal to I alpha, and I for the rod, it's already calculated, or a well-known constant. It's equal to 1/3 ml square. Now alpha for this part equal to the torque, or the net torque, over I. In other words, mg L over 2 divided by 1/3 ml square, or 3g divided by 2L, and this is the angular acceleration. Now to find the linear acceleration, A tangent here, it's equal to R alpha, and R in this case it's equal to L. You substitute this, you will find A tangent equal to L alpha, or equal to 3/2g. Now in this model, the situation is quite different. We have here a solid sphere as a pulley, and we have here a mass hanged by this rope, this one here. In this case, we would like to calculate the net torque and the angular acceleration and the tangential acceleration. Now we have here tension, and we have here weight mg in this case. So the net torque equal to I alpha, which equal to TR, and T in this case it's not equal to mg because this object is moving downward. We have to calculate here the tension. Now alpha is the angular acceleration, it's equal to TR over I is the moment of inertia for this solid sphere pulley. Now sum of all forces on Y equal to ma. Now since the object is moving downward here, we have an acceleration, tangential acceleration here. Now mg minus tension, it's equal to ma, or in other words, A it's equal to mg minus tension over m. Now A is equal to R alpha, or equal to TR square over I. In other words, mg minus tension over m. You solve this one here, you will find that the tension equal to mg divided by 1 plus mr square divided by I. M in this case is the object mass, and R is the pulley radius. You substitute number, the tension is almost equal to 12 for this case, and the torque will be equal to almost 17.64 Newton per meters. By substituting the tension in alpha, we can find the angular acceleration, and again we can find the tangential acceleration. Now let's move on and modify the polytype and make it spherical shell. As we can see here, the net torque we obtained for this spherical shell is different from the net torque we obtained for solid sphere, because the tension, let's write it down, the tension we just calculated before, it's equal to mg over 1 plus mr square over I. So the tension depends on the moment of inertia of the pulley itself. For the solid sphere, it's equal to 2 over 5 mr square, and for spherical shell, it's equal to 2 over 3 mr square. For that reason, the net torque here we obtained is different. Let's continue. For solid cylinder, we should obtain different net torque and different alpha and different tangential acceleration. This one here, 2005. And this one for cylindrical shell, 27.56 Newton meter. Example: a wheel of radius r, mass m, and moment of inertia I is mounted on frictionless horizontal axle. A light cord wrapped around the wheel supports an object of mass m. Calculate the angular acceleration of the wheel, the linear acceleration of the object, and the tension of the cord. Let's graph the situation here. So here's the wheel with mass capital M, and the radius for this wheel, it's equal to r. And here's the rope, okay, connected with mass M. Now we have here tension, and the weight for this mass is equal to mg. Now to calculate the angular acceleration of the wheel, let's calculate the net torque equal to I alpha. And we also know that the net torque it's equal to r cross f. R in this case here is the radius for the wheel, and F in this case is the tension. So the net force it's equal to tension R, and the angle between the radius and the tension, it's 90 degrees. Sine 90 equal to 1. So there's no need to say sine theta in this case here. So alpha is the angular acceleration, it's equal to T is the tension, R divided by I. Now sum of all forces equal to ma. Now the forces on this object here, we have tension, we have mg. Now since the object is moving down in this one here, so we can say that mg minus tension, it's equal to ma. Now in this case here, mg minus tension, it's equal to ma, and a in this case is the acceleration or linear acceleration, it's equal to mg minus tension divided by m. Now the relation between the angular acceleration and the linear acceleration is a equal to r alpha. In this case, alpha equal to tr over I. In other words, t r square over I, which equal to mg minus tension over m. Now the tension in this case, it's equal to mg divided by I plus r square over I. Now use the obtained results. A in this case, it's equal to G divided by I plus I over mr square, and alpha equal to A over R, which equal to G divided by R plus I over R. Example: two blocks having masses m1 and m2 are connected to each other by light cord that passes over two identical frictionless pulleys, each having a moment of inertia I and radius r. Find the acceleration of each block and the tensions T1, T2, and T3 in the cords. No slipping between the cord and the pulleys. Let's draw the situation. So we have here the disc, and we have pulley 1 and pulley 2 connected the rope here. This is M1, and this M2. We have here T3, T2, and T1, and it's moving this way here, and this one is moving this way here. Now let's draw the free body diagram for this one here. So M1 have tension T1 and weight M1G. Now the free body diagram for this one here, this is M2. We have again M2G, and we have tension 3. Now let's also draw the free body diagram for the pulleys. Now on pulley 1 here we have T2, we have T1, we also have the weight for this pulley, and we have the normal to the central axis of the pulley. Same situation for the other pulley, this one here. In this case we have T2, T3, and pulley G at the normal and 2. Now let's apply Newton's second law. M1G minus tension 1 equal to M1A. This first equation here. And T3 minus M2G equal to M2A. And this is equation number 2. Now let's use the torque equations here. Remember, the net torque, it's equal to Fr, which equal to I alpha. The net force for pulley 1, it's equal to T1 minus T2 times R equal to I alpha, and T2 minus T3 times R equal to I alpha. So this is the third equation, and this is the fourth one. Now by adding equation 3 and 4 together, we will find out that T1 minus T3 times R equal to 2I alpha, and if we add this equation and this equation here, you will find out that T3 minus T1 plus M1G minus M2G equal to M1 plus M2A Just rearrange this equation here. T1 minus T3 equal to M1 minus M2 G minus M1 plus M2 G Now you substitute this back in this one here, you will find out that M1 minus M2 G minus M1 plus M2 A all multiply by R equal to 2I alpha, and we all know that alpha equal to A over R. So in this case, M1 minus M2 G minus M1 plus M2 A equal to 2I A over R square, or in other words, A equal to M1 M2 G divided by M1 M2 plus 2I over R square. Now notice that if M1 greater than M2, it means the acceleration is positive, which means the left block accelerates downwards. But now acceleration here is positive. But if M1 is less than M2, in this case the acceleration is negative and the right block will move downward. And if M1 equal to M2, it means acceleration equal to 0. Now to find the tension T1 and T3, you just substitute the acceleration back in the above equations. You will get T1 equal to M1G minus M1A equal to M1G minus A, or M1 times G minus M1 minus M2 G divided by M1 plus M2 plus 2I over R square, or 2M1. You just rearrange things here, times M2 plus I over R square divided by M1 M2 plus 2I over R square. Now same procedure to find T3, in this case here, equal to M2G plus M2A equal to 2 M2G times M1 plus I over r square divided by m1 plus m2 plus 2I over r square. And finally, to find T2, it's equal to T1 minus I alpha over R, or equal to T1 minus I A over R square. You substitute T1 from this one here. It's T1 here. You substitute back in here, equal to 2m1 G times m2 plus I over R square divided by m1 m2 plus 2 I over R square, this one here, minus I over R square. Now we need to substitute A from this one here, times m1 minus m2 G divided by m1 plus m2 plus 2 I over R square. You just simplify this final equation, you will find out that 2m1 m2 plus m1 plus m2 times I over R square divided by m1 m2 plus 2 I over R square, all multiplied by G, and this is actually T2. Example: a uniform rod of length L and mass M is free to rotate on a frictionless pin passing through one end. The rod is released from rest in the horizontal position. What is its angular speed when it reaches its lowest position, and what is the tangential speed of the center of mass and the tangential speed of the lowest point on the rod when it's in the vertical position? Now let's graph the situation. Now here's the situation. At this position here, the energy we have here is potential energy, and E in this case initial equal to just potential energy, or mg. Now the distance from the center of mass equal to L over 2. Now at this final position here, the energy we have here is the rotational kinetic energy, which equal to, in this case, E final equal to K rotational, or half I omega square. Now from the conservation of mechanical energy, K final plus U final equal to K initial plus U initial. Now there is no initial kinetic energy, not even final potential energy. In this case, half I omega square equal to half mg L. Now I for this rod, as we mentioned before, it's already calculated, so equal to half times 1/3 ml square omega square equal to half mg L. You just simplify this equation here, the omega equal to square root of 3g over L. Now to find the tangential speed of the center of mass and the tangential speed of the lowest point on the rod when it's in the vertical position, let's find first the V center of mass. In this case, it's equal to R omega, or equal to R is the distance between pivot and the center of mass. It's L over 2. This is R. And omega, we just calculated this one here, so equal to square root of 3g over L. By simplifying this equation here, so V center of mass equal to half square root of 3g L. Now at the lowest point here, the only difference here is the distance r in this case. Now in the previous case it was L over 2. Now in this case here it's the whole length L. In this case V equal to 2V center of mass, or in other words V here equal to square root of 3GL. Now let's have in this interesting case, we have here two masses. One of them is 2 kilograms and the other one is 3 kilograms. And the poly here is a solid sphere with radius equal to 1.5 meters, and the mass for this poly is equal to 5 kilograms. Now let's see what's gonna happen here. Let's start this one here. Now as we can see here, the net torque it's equal to 4.2, and the angular acceleration is this one here, and the tangential acceleration it's equal to 1.4 meter per second. Now let's analyze the situation. Now for this object here, the 3 kilogram one, we have two forces: weight, it's m1g, and tension. In this case it's equal to tension 1, and remember this tension is different than this one here. Now in this case here we have weight m2g, and this is tension 2. Now let's start the analysis. Sum of all forces here, it's equal to ma. Now m1g minus tension 1, it's equal to m1a, and again this one here, tension 2 minus m2g, it's equal to m2a. You add these equations together, you will get this one here, m1 plus m2a equal to m1g minus T1 plus T2 minus M2G, or simplify this one here, T1 minus T2 equal to M1G minus M2G minus M1 plus M2A. Now let's leave this one here. Now remember, for this poly here, we have T1 minus T2 times the radius r equal to I alpha. You substitute T1 back in this one here, you will find that now just substitute the numbers, you will get A equal to 1.42 meter per second square. Once we calculate the acceleration, we can easily calculate the angular acceleration. And remember, A, it's equal to R alpha, and alpha equal to A over R. And once we calculate A, the net torque equal to I alpha, and that's it. The tangential acceleration equal to 1.42 meter per second, alpha it's equal to 0.93 rad per second square, and the net torque equal to 4.2 Newton meter. Now if we modify the pulley and use spherical shell, in this case here, the spherical shell, we will get different outcomes than the one we get for solid sphere. Now for spherical shell, the net torque it's equal to 5.88, and alpha it's equal to 0.78, and A it's equal to 1.18. And remember, all these parameters depends on the moment of inertia. Now this is for solid cylinder. And this is for cylindrical shell. Consider two cylinders having different masses M1 and M2 connected by a string passing over a pulley. The pulley radius R and with moment of inertia I about its axis. The string does not slip on the pulley and the system is released from rest. So here's the situation. This is the pulley here and with radius R, and we have here two cylinders M1 and M2. Now M1 drops from height h, as we can see in this case here. The question is, find the linear speeds of the cylinders after cylinder 2 descends through a distance h and the angular speed of the pulley at this time. Now again, from conservation of mechanical energy, K final plus U final equal to K initial plus U initial half M1 V final square plus half M2 V final square plus half I omega final square plus, now the potential M1 GH minus M2 GH, all equal to 0 plus 0. No kinetic, no potential energy, no initial kinetic or initial potential energies. Now you simplify this equation here, you will find out that half M1 V final square plus half M2 V final square plus half I over R square V final square equal to M2GH minus M1GH. In here we used V equal to R omega. You simplify this one here, you will find out that V final equal to 2 M2 minus M1 GH divided by M1 plus M2 plus I over R square to the power half, and omega final in this case equal to V final over R, or in other words 1 over R times 2 M2 M1 GH divided by M1 M2 plus I over R square to the power half. Let's consider this situation. We have a solid sphere rotating on an inclined surface but not slipping. In this case here, we would like to calculate the translational kinetic energy and rotational kinetic energy at the bottom. Let's assume we have here a point P on the outer surface of the sphere. So the kinetic energy equal to half IP omega square. In such a way, IP is the moment of inertia about a rotation axis through P. Now we use parallel axis theorem. Therefore, IP equal to I center of mass plus mr square. Now remember, this is the center of mass and this is the rotation particle on the outer surface of the sphere. So, therefore, the kinetic energy is equal to half I center of mass omega square plus half omega V center of mass square. Don't forget, V equal to R omega. You substitute this, you will find half I the center of mass over R square plus half the center of mass square, or half I center of mass over R square plus is I center of mass, V center of mass square, conservation of energy, K final plus U final equal to K initial plus U initial. So K initial 0 and U final here it's equal to 0. Therefore, half I center of mass R square plus the center of mass square plus mgh. Rearrange this one here, you will find that V center of mass equal to 2gh over 1 plus I center of mass over mr square to the power half. Once we find the V center of mass here, we can find the translational kinetic energy and the rotational kinetic energy. So the kinetic energy and translational energy started from 0, and as we can see here, it's increasing. Here is the rotational kinetic energy and this is the translational kinetic energy. It's increasing until it reaches the bottom of this inclined surface. One last example. For the solid sphere rolling over inclined surface, calculate the linear speed of the center of mass at the bottom of the incline and the magnitude of the linear acceleration of the center of mass. So here's the situation. We have here an inclined surface and a sphere rolling over this inclined surface here. The radius for the sphere is equal to r, and again it's solid sphere and it's rolling. Now since it's rolling, it has angular velocity as in here, and this is the center of mass, v center of mass here. So the distance here, this is x and this is theta, and the height for this inclined surface is h. Now the kinetic energy, it's actually rotational kinetic energy, it's equal to half I center of mass times v center of mass over r square. Remember, omega equal to v over r, plus half v center of mass square. The ball here is actually having two kinds of kinetic energies: rotational kinetic energy and translational kinetic energy. So the rotational kinetic energy, it's equal to half I omega square, and the translational kinetic energy, it's equal to half v square. So in total, k here, it's equal to half times I center of mass divided by r square plus m here v center of mass square. Now this one here is actually at the bottom of the inclined surface. At the top of the inclined surface, we only have potential energy, no kinetic energy whatsoever. In this case here, the k final plus u final equal to k initial plus u initial. Now this part here, we just calculated this from this one here, and no kinetic energy at the beginning of the motion. So the only energy we have here is the potential energy. In this case, half I center of mass over r square plus m v center of mass square plus 0, again no potential energy at the bottom of the inclined surface, equal to no kinetic energy at the beginning of motion plus mgh, only potential energy we have at the beginning. So v center of mass in this case equal to 2gh divided by 1 plus I center of mass divided by mr square to the power half. That's it. Thank you for watching.